Here we go. All right, now that, so we've got this bare piece of paper back, but so basically when we're talking about different sorts of solutions, when you do shear, load shear and bending moment, which is, like I said, mechanics of materials will build directly on this material. As a matter of fact, you will do this exact same material when you begin mechanics of materials, and we'll expand on it a little bit. So there's a real, there's a good solid reason for us spending some time getting to know this. But the solution for these types of problems looks like 3 stacked diagrams. One is the load diagram, one is the shear diagram, and one is the bending moment diagram. All right, now, oops, there we go. So the load is going to be measured in units of force. Shear is going to be measured in units of force. And moment is going to be measured in units, I should say force acting through a length, so, or force times a length. Okay, and they should stack on top of each other for your solution. All right, so why I'm repeating this is because that's how everything has to look, and that's actually what you're graded on. So you need to, you start by constructing this based on a free body diagram, right? You put in the reactions, you find the equivalent loads, and you build that. Then shear is determined from that load diagram, and the moment diagram is determined from the shear diagram. And we've talked about how you do this using that technique that I've referred to as a cutaway, where you, every time something changes on the beam, you take slices of that beam up to that point, and you think about what's happening in terms of shear and what's happening in terms of moment. Then I had also advised you that you always cut on the right. And as Oz pointed out, you do not have to cut on the right. This is just a keep your signs straight idea. Okay, that's it. So when you cut on the right, you always draw your shear, which is labeled V, pointing down in order to maintain a sign convention. And when you do a cutaway on the right, you always do a moment responding this way. Okay, now here's one little thing you can always think about. When you have a moment that tends to bend a beam like this, this is a positive moment. When you have a moment that tends to bend a beam like this is a negative moment. So depending, if you do choose to cut on the left, start from the right and on the left, you still need to keep that sign convention in mind. Okay, easy way to remember. Positive is smiley face. So if you're feeling positive, you draw a smiley face. Negative is a frowny face. So you can do it that way as well. Just to remind yourself, wouldn't use it as a final solution, but it's a nice check sometimes just to make sure that you're on the right track. So when you do a cutaway, one of the main issues is sign convention. Okay, but so I've said the load diagram follows from the free body diagram, which you don't really draw as part of the solution. And then the shear diagram follows from the load diagram, and the moment diagram follows from the shear diagram. So then the next question becomes, or might become, what is the relationship between load, shear, and moment. Okay. There we go. All right, well, that is outlined here in section, here it is, 7.3, which is the last section that we cover. All right, and now to be honest, you can always just draw the diagrams and do cutaways. There's no reason not to do that. But sometimes, as an enhanced solution technique, doing the purely mathematical solution is easier. And sometimes using them together is easier than anything else. So the first thing we have when we look at this is that we see dv dx is equal to minus w. What does that mean? It means the first derivative of shear with respect to x is the negative of the distributed load. Okay, so if you recall, little w is equal to something in force per distance, okay? So this is a little bit complicated, but if it's a smooth function, what does that mean? Well, if w is smooth, and if it could be smooth throughout, or it could be just smooth over an area, we can take that derivative equation, separate it, and then if the load curve were linear, we could just say v at point 2 minus v at point 1 is equal to minus w times x at point 2 minus x at point 1. If and only if omega is constant. If it's not, we can plug in a function. So maybe omega is some function of x. All right. Then when we get to this point, we would have dv is equal to minus, let's just call this we should just call this w as a function of x, okay? Minus w as a function of x dx. Then when we integrate this side, we would have b2 minus b1, but over here, we would have to take the integral of whatever that function looks like. So if it's y equals mx plus b, in other words, if it's a straight line with a slope, we could plug that in there. Or if it was something else, like this whoop-de-doo, it is straight, it is continuous, but it's not straight. If we had something that called out what that function was like, you could just plug it in here, do the integral between those 2 points. These are always definite integrals. And we would have our answers. So if you do that, you do have v2 minus v1. What this also tells you is that the difference in v, so in other words, the shear at one point at the end, let's say, at the end of whatever piece of that curve is smooth, minus shear at the beginning, is the area of the load curve. So in other words, this is the load curve. And so the relationship here is that v2 minus v1 is the area under, not the shear curve, but the load curve. So if we have the area under the load curve here, we know that that's going to be the difference between shear at point 1 and shear at point 2. So how could you find the area? Well, you can just find the area in any of the ways using Newton-Raphson or any sort of a finite difference, or integrating the curve. Whatever skills you have available in your math toolbox. All right, conversely, what is this saying? This is saying the negative of the load curve is the first derivative of v with respect to x. The load, the negative of the load, distributed load, is the first derivative, which is another way of saying slope of the shear curve. Okay, so going down, you have an area, which is an integral. Going up, you have a slope, which is a derivative. So integrate, differentiate, area, slope. Okay. So what do you think is going to happen with the moment curve? Not based on your mad math skills, but just on like the correlation that I'm trying to draw here. Yes, that's it. You've got it. So if you turn the page, you'll see the same sort of relationship. Shear is equal to dm dx, or shear is equal to the slope of the moment curve. The area under the shear curve is equal to the difference between the moment at the end and at the beginning. Okay, so it's the same idea right here. Okay, so the first derivative, which is slope of the M curve, is V. And going the other way, the area under the shear curve is delta M. Right? So if you have a continuous function over all or part of a distributed load, you can use these ideas as well. So, what questions do you have? All this really does is gives you an extra tool in your toolbox. Now, if you have point loads like this, the mathy piece, the 7.3 material, is harder to use. If you have distributed loads like this, the integral / differential stuff is easier to use. This is my W, and it is a function of X. At point B, I see that, let's do this, W at B is equal to 2.4 kilonewtons per meter. W at C is equal to 6 kilonewtons per meter. What kind of a function is this? Straight line? Does that, yeah, so it's a linear function. And we know that this is a straight line. And so the nature of this function is y is equal to mx plus b. So we would have to find out what that is. Okay, how are we going to do that? Well, I can find the slope. M is delta y over delta x. So I go, my delta y goes from 6 to 2 between however many feet we have here. Oh, here it is. B to C is, this is at 4 feet. At 4 meters, excuse me. And then whatever that does, I've lost that page. Here it is. Maybe it's right here. There we go. Let's see. Six. So this is a total of 6. So this is at 4 feet. And this is at 10 feet, right? So 10 minus 4 gives me 4/6, which is 2/3. Okay, so my slope is 2/3, 2/3. Now, if you think about it also, this is positive. If you remember, slopes are positive if they go up the way that you read, in other words, over to the right, negative if you go down, 0 if they're flat, and undefined if they are vertical. All right, so we have that. So then how are we going to find my y-intercept, my b value? Well, I'm going to plug in any value of y and x. I can see here that I have a value of y equals 6 at x equals 10. So I could plug that in and I could say 6 is equal to 2/3 times 10 plus b. 6 is equal to 20/3 plus b. 6 times 3 is 18. So that's like 20/3. If I put this, that'd be 6 times 3 would be 18. So I get minus 2/3 equals b. So my final equation for this would be y is equal to 2/3 x minus 2/3. Right? So then I have something that I can integrate and differentiate, right? All right. So if you look at that, continuing with that thought, just looking at this, that's exactly what they've done, right? If you go back to those original equations in 7.3, oops. I see that dv dx is equal to minus w. This is w. In other words, if I plug in those variables, I would get w is equal to 2/3 x minus 2/3, right? So then I can take that equation, which tells me dv dx equals minus w, which equals minus 2/3 x minus 2/3. So I can say dv over dx is equal to minus 2/3 x plus 2/3. Okay, and then I separate dv is equal to minus 2/3 x plus 2/3 dx, and integrate. I have to be careful of my limits. This is going to be v at 10 feet, and this is going to be v at 4 feet, or 4 meters, pardon me. And this is going to be 10, and this is going to be 4. So in this section, I can do those integrations. Okay, I can find those points. I can also find where it crosses E, which is the point where there is no shear. Okay, so there's and then because that becomes the slope of this, I also know that my slope is going to be 0 at that point, which is going to be a horizontal line. So you see, I can kind of work through that, come up with that final answer. All right. And that's just kind of nicely summarized right here. I really like in this Beer and Johnson tech book, the solving problems on your own. It usually takes everything that you've done and has it nicely put together for you, along with the steps for how to go through and solve those problems. All right, what questions do you have for me?
So that doesn't work very well if you have a specific point.
Right.
Yeah.
If you have a specific point, it's easiest to do cutaways. Absolutely. You can still do it. Like, I'll do this really quickly for you, but like, let's just say that you had a beam. This is your, and you've got a reaction at A, and then like a rolling reaction here at B. And if you had a force of 10 kilonewtons here, let's just say that this is 6 meters and this is 4 meters, right? Okay, you could say you need to find R sub A and R sub B, so you'd say summation of forces y equals 0, R sub A plus R sub B equals or minus 10 equals 0. So R sub A plus R sub B equals 10 kilonewtons. Then you would find R sub A or R sub B by doing moments. So you could say summation moments about point A is equal to 0. So this is going to produce a clockwise or negative moment. So negative 10 times 6 is equal to plus R sub B times 10 is equal to 0. So you get negative 60 plus 10 RB equals 0, or RB equals positive 60 divided by 10, or 6. So this is going to be 6 kilonewtons. This is going to be 4 kilonewtons. Okay. So then if you were doing cutaways, first of all, you would draw this be your load diagram. You have R sub A here, which is 4 kilonewtons. Here at 6 feet, you'll have 10 kilonewtons. And over here, you would have 6 kilonewtons. All right. Then if you're going to think about this in terms of that V diagram, the easiest way for me to think about it is just like if I do that cutaway and I get a V, I get from here to here, 4 minus V equals 0, 4 equals V. So for me, the easiest way to do that is just like that, right? Then from here to here, on the other side of that 10, we get 4 minus 10. My cutaway would still be down. Minus V equals 0. Minus 6 minus V equals 0. Minus 6 equals V. So at this point, it would just go down here. So this is positive 4 kilonewtons, and this is negative 6 kilonewtons. Okay, but now, if you think about it, you can still do the integral, because what you get is V2 minus or Vd, which would be up to this point. All right, excuse me, let's get this down. Minus Vc, which is 4, equals minus W dx. Okay, so what is W? Well, it's just, you just have 4 is all. So you have 4 minus 0 equals 4 is what it amounts to. And so then all the way across here, it just remains 4. So you can still do it, but it's a little more math than you need to do. So yeah. And it's kind of the same with the moment diagram, because from here to here, the force, the moment's going to go like that. So from here to here, you'll get 4 times x plus m equals 0. But this is going to go that way, so it's minus 4. So you get m equals 4 times x. So from here to here x is 0, here x is 6. So it's going to go from 0 to 6 times 4, which is 24. And that would be in kilonewton meters. Okay. And it's linear because once again, the slope, and then it does the same thing. It just comes right back there. So yeah. And actually these 2 points should be right underneath each other. That's just my drawing skills. I think I just put blue ink all over my face too. So anyway. But yeah, so I guess when I approach these, if they're point loads, I generally just do the non-calculus method. If they're distributed loads, if the distributed load, I always at least think about the calculus, involved in it, just to make sure I get the shape of it correctly. But I still like to do the cutaways to get my sign convention. So
doing the numbers distributed across, it's distributed across like 6.
yeah.
Also use the cutaway method at like.
Yes, absolutely. So like if you had something like this, I think is what you're asking me, like from 0, let's just say this is 0 feet and this is 10 feet, just to make it easy. And you have some W that looks like this. Is that what you're talking about? Okay, and let's just say the W is 2 pounds per foot. Okay. All right. So then what's gonna happen is, okay, if we think about doing a cutaway, let's start here at 1 foot, okay? At 1 foot, the total load prior to that would be 2 times 1 foot, which would be 2 pounds. So you know that your load, I mean, your responsive load here, so you would have your W times X right here, and then V. So you would get WX minus V equals 0, or WX equals V. So what that means is here, X is 0. Here, we go to 2, and we would continue going up, right? Yeah, and so that was how you would build up this load curve.
And then we'll just start like right in the middle too, right? You're just doing-
Exactly, yep, yep, or yeah, that's what that's gonna look like. So then with your moment, you're gonna be thinking about the slope. Here, the slope is 0. So that's gonna give you a 0 moment. So your moment is gonna be kind of curved like that, or it could possibly be straight like that. Yeah. So you can kind of pull together those different ideas of what that should look like. I was gonna see if there was a good example here of a distributed load throughout. This is a little bit more complicated, but there's some good stuff here. If we just look at the first section of the bar, you have a reactive force here, right? So you draw the shear curve, oh, and I forgot my reactive force. Sorry about that. That was bad. I just pretended like there was nothing holding this up. So that is not true. See what I did? There has to be a reactive force here and here. I just decided there wasn't. So it's just, I don't even know what it's doing. So you will have that reactive load here. So the V is going to respond to it, and then it's going to decrease throughout the end of this. If you were to do, so really this would be like this. You'd start here, it would go like that. And that would be in the middle, all right? And then the moment is going to be curved. It's actually a parabolic because it's a WX or a VX dx. So it's a VX squared over 2. So then this one, the moment curve would be, it would start at 0 because there's no moment arm, and it would curve up to the middle where that would be equal to 0, and then it would come back down again to 0. So that's what the shape would look for a load fully distributed across that. Yeah, but one has to remember, unlike their teacher, that there are going to be reactions, because if you don't have any reactions, it's just gonna, I guess, float away in space. This way I had decided it was going to work today. So, all right. All right, any other questions? Joey needs a little nap today. So, all right, well, I'm gonna go ahead and turn off the recording. There we go.